Thank you, Tom. Good afternoon, all our participants. My name is Nicola Cairo, Project Officer at ETN Global, a non-profit membership association in the field of energy and turbo machinery, and also the coordinator of the EU-funded project Robinson. Today, you have been invited to a new training module on the life cycle assessment tool, which has been developed by our project partner, Paul Scherrer Institut. Today, we have our presenter, Tom Terlouw, researcher at the Paul Scherrer Institute, who will present us a tool to optimally design multi-energy systems on geographical islands. Our project is aiming at developing a new energy management system at the demonstration island of Eigerøy in Norway and also in the follower islands of Western Isles in Scotland and Crete in Greece. So with no further delays, I'd like to give the floor to our presenter. Following Tom's presentation, we will dedicate about half an hour for question and answers discussions, where not only you will be able to ask any questions you may have or also comments, but also you can interact and also highlight any other tools that you are aware of on the market. So with this, I'd like to give the floor to Tom for his presentation. So Tom, the floor is yours. Thank you very much.
Yeah, thank you. Thank you, Nicolo, for the introduction. And thank you for joining today, of course. Very nice to see many of you online. So today I'll give an overview of what we did during the Robinson Horizon 2020 project, and more specifically about designing Robinson Islands by integrating techno-economic and life cycle assessment. As Nicola already said, I'm Tom Terlouw. I'm a researcher at the Paul Scherrer Institut in Switzerland. And yeah, I worked on this project during my PhD, and really fascinating project. And I liked, of course, to give a presentation about that today. So I will start with an introduction. Yeah, I will start with an introduction, showing the background on why we did this, of course, as well as the motivation. I will continue with the methods, where I explain about optimizing decentralized energy systems, or which are also called multi-energy systems. Then I will come to the next step, where I talk about the open source repository and framework to optimally design decentralized energy systems, such as geographical islands, which is called Optimes, and this is already online, this repository and framework. We show how we can apply this framework on two case studies, the case studies on Eigerøy in Norway and in Crete in Greece. And these are, of course, the islands also involved in Robinson. I will continue with the limitation of future work, and I will end with the key messages and an overview of the results, let's say. So first, a little bit of background. Everyone is aware, of course, that we have changing climates. We have a rise of global CO2 emissions, which also leads in a rise of global temperatures. And as a consequence, we have more extreme weather conditions. For example, we have more heat waves, more droughts and wildfires. And also as an ultimate consequence, we also have biodiversity losses. And over the past few years, we also had a geopolitical situation which was not entirely stable, I would say. We had an energy crisis, of course, especially during the pandemic. And we also had infrastructure attacks. And this, of course, leads to us that we need to shift from fossil fuels to renewable energy sources. And this requires the integration of low carbon energy carriers into the entire global economy. And on the right-hand side of this slide, you actually see that, of course, in the past, we used a lot of fossil fuels, and we should shift now away from that to more renewables. And by doing this, we should also phase out more centralized fossil power plants and shift more to decentralized energy systems. And this has also been suggested in the literature. And by shifting to more decentralized energy systems, this allows us, of course, also to consider location-specific boundary conditions, but also location-specific renewables. And on the bottom figure, we also see, of course, now that in the future, we hope that we're going to integrate more renewables and so on. So where then come decentralized energy systems into play? As I said, decentralized energy systems are needed to move away from centralized fossil power plants, let's say, in a way. And decentralized energy systems can also be called multi-energy systems because decentralized energy systems usually integrate different energy carriers. And on the right-hand side of this slide, you see an example of a multi-energy system installed on a geographical island. And this is on the island Aigeroy. What is good to remind here is that it looks complicated, it maybe also is, but it's good to remind that we have different energy carriers in such an energy system, for example, electricity, heat, syngas, and hydrogen, but also that there are a lot of different technologies involved. And these technologies should be involved, of course, to decarbonize the system. And we also can integrate short-term energy storage, think of, for example, about batteries, but also more longer-term energy storage, think about, for example, hydrogen storage. And what is also good to mention here is that such a system can be grid connected, so that means connected to a power grid, but they can also be designed as off-grid solutions, so that means that there is no power grid connection, and that there is also no natural gas grid connection. And the motivation of us was to do this, to install, let's say, a multi-energy system on a geographical island is, of course, to decarbonize, but also at the same time try to improve the economics of such a system. And already during the design phase, so before you're going to install such a system, it's useful to determine what the potential costs and life cycle around the impacts are of such a multi-energy system. And therefore, it's needed to, for example, develop models as we did. What has been usually done in this kind of models is that they were usually focused on cost or that they included environmental aspects in a simplified way. For example, a lot of models, they include operational CO2 emissions, but they don't include emissions, for example, from system components, also so-called embodied emissions. And also, in addition, they usually focus on greenhouse gas emissions, and they usually are not focusing on other environmental impacts. So environmental impacts go further than life cycle greenhouse gas emissions. For example, think about human toxicity, materials, water consumption, and so on. And why this is interesting for geographical islands, like in the context of Robinson? Well, geographical islands can be a demonstrator of decentralized multi-energy systems because they're usually isolated and they also aim at full decarbonization. And we also have a real demonstration project within Robinson Horizon 2020, which is in Aigeroy. And as Nicola already mentioned, we also, of course, have follower islands, which are Crete and Western Isla. And we try to have here like an integrated approach. So we're not only focusing on one sector, but we try to have like to involve different energy sectors here. So we have a residential energy sector involved, industrial energy sector, and a personal mobility sector we included. Then a bit more about how such a system looks like. As I said, we include different energy sectors. Besides residential households, we also include industry, and industry is usually more complicated because we need high temperature heat for industry, and high temperature heat cannot be delivered by all different kind of technologies. So, for example, high temperature heat provision, you could, for example, use boilers. And what is quite interesting within Robinson is that we also try to integrate an advanced combined heat and power unit, which is able to run on low carbon energy fuels, like, for example, syngas, hydrogen and biogas, which are then mixed in a gas mixer. And this can then be used as low carbon fuels into the advanced heat unit to decarbonize high temperature heat. And this has also been done. And I think this is quite interesting, which you also see in this figure on the right-hand side here. And as I said, this can be used to decarbonize the high temperature heat supply, but also can be used, of course, to generate some electricity. And I mentioned already before that different energy storage solutions are considered, like, for example, batteries, hydrogen, and residential heat storage in this system. And what is also important to mention here is that hydrogen can be an important component in such a system. And hydrogen can be generated by, for example, electrolyzers driven by low carbon electricity. And hydrogen can be stored, it can be exported, of course, for example, to be used in ships and so on, or even vehicles. But it can also be used in advanced CHP unit, as I said, and therefore hydrogen can be an important component for this multi-energy system. So then a little bit more about the specific methods used. So as I said, our goal is already during the design phase to optimally design such a system in a cost-effective and environmentally friendly way. And we did this by using a mixed integer linear program, which is a mathematical approach to design such a system in, for example, cost-optimal way or an environmental optimal way. And we did this by considering all technologies on the previous slide. And for each technology, of course, we considered different constraints, for example, constraints related to efficiencies, part load ratios, ramp up and ramp down, as well as minimum up and minimum down times are considered. And for ramp up and ramping down and minimum up and down times, these are only applied for a couple of technologies because they really increase the complexity of the linear program a lot, of course. As you also can imagine, of course, in such a method, there's a lot of data involved. We need a lot of techno-economic data. We need also life cycle analysis data, and we need hourly data for generation profiles and demand profiles. And I didn't mention LCA, but the specific interesting part of our framework is also that we endogenously integrate LCA into our framework. And LCA is described as a process to assess products or services over the entire lifetime to determine the overall environmental impacts. So here we're not only focusing on operational greenhouse gas emissions, but we also include embodied emissions, let's say. And as I said, here the main novelty is also to integrate LCA endogenously into the optimization problem to also determine life cycle greenhouse gas emissions and other environmental burdens in a post-LCA. And yeah, and then I want to explain a little bit more, what kind of input data we need, in this tool which we developed. So as I said before, there's a lot of data needed. First of all, we need data on the weather conditions, which is hourly data. Our optimization runs over the entire year, so 8,760 hours. So we need hourly data regarding wind speed, temperature, and solar radiation. As you can imagine, wind speed and temperature is also mostly needed, of course, also for the wind turbines, and solar radiation, temperature, wind speed also for solar PV. We also need hourly energy prices, especially for power, heat, and hydrogen are actually single prices, same for biomass. And we need demand profiles, so we need electricity demand profiles from the residential sector, from the mobility sector, from the industrial sector. And as I said, we should also make a distinction here between low temperature heat and high temperature heat requirements, because high temperature heat requirements cannot be met by all the technologies within the system. Furthermore, we need techno-economic performance data, as I said, so the capital expenditures, operation and maintenance, lifetimes and discount rates. And for the environmental analysis, we need the lifecycle inventory database, and here we used EcoInvent for that. And as such, what is returned from the optimization. These are also called the decision variables, which are the optimal installed capacities of technologies. And these are all the technologies which I showed before on the slide. The commitment status of conversion technologies, the startup and shutdown status of conversion technologies, input and output power of storage and conversion technologies, energy storage and energy storage technologies, and import and export of energy. And as you can see here, there's a lot of variables, and most of them are also on an hourly basis. So we have a lot of variables which are returned. And as I said already before, the main objective here are annual cost and life cycle greenhouse gas emissions. So it's a multi-objective optimization problem, but of course it can also be applied as a single objective optimization problem. Furthermore, what we also have to consider in this kind of frameworks is location-specific boundary conditions. For example, we have a maximum amount of biomass availability into a region, but also a maximum amount of renewables which can be installed. So then I will want to elaborate a little bit more about our framework, which we recently published on GitHub. And because we published it on GitHub, the nice thing is that it's open access, so everyone can use our non-confidential data and also the code. And we also gave a nice name to the repository and framework, which is called Optimus, which stands for the Optimal Design of Multi-Energy Systems. However, at this stage, you still need, I would say, Python knowledge to really apply it, and you also need some kind of licenses, and I would like to go through that quickly, right? So first of all, you need to retrieve day-ahead electricity prices. So for the end ENTSO-E, which is kind of the power grid operator within Europe. However, this is free of charge. However, you need also a key for premise, which is needed to generate prospective LCA database. However, we made an option available that is not really needed to use this key. So you could also set one variable to false, and then you can just only use greenhouse gas emissions, but you cannot calculate other environmental burdens. However, to calculate the impact factors, the LCA impact factors yourself, you need, of course, eco-event. And this might be a bit more tricky maybe for most of you, because the eco-event database, in my opinion, is not so expensive, but of course you still have to invest in such a license. But as I said, if you want to focus on greenhouse gas emissions, then you can set the parameter, which I showed here, to false, and then you don't really need this. Another thing which you need is a Gurobi license. This is really needed to, of course, do the optimization itself. And you need to install a lot of open source Python packages. So this is, of course, all open source, except of the Gurobi license and the eco-event database. But as I said before, the drawback is that you need to be familiar with Python at this stage. And this is, of course, a little bit more difficult for maybe some of you. But if you find it still interesting, you can still go to our repository and have a look. So I would invite you that you see the link over here. And yeah, if you have any feedback or ideas on how to improve, please let me know. And now a little bit more on how the optimization has been done within the framework. So the actual optimization is performed in the Python function, because, as I said, we use Python to do so, which is called optimize mess. And as discussed, however, to optimize such a multi-energy system, which can be quite complicated and could involve a lot of different technologies, you need a lot of hourly data, techno-economic data, and environmental data, including technology limits, which you also see the right-hand side, right? What you discussed before, you need weather conditions, energy prices, demand profiles, techno-economic performance, and so on. And I just made a screenshot on how that looks, in code. Here, of course, I also documented it well, but yeah, it's still in Python, so maybe not so easy for every one of you, but still, I thought it's nice to make a screenshot here. And now a little bit more, what we can do with the framework. So, of course, from the framework, if you optimize a multi-energy system, you get different outputs, which are the decision variables, which are already quickly discussed. And as I said, we also get the optimal sizes of all energy technologies within the system boundaries. We also get let's say, the optimized hourly system operation of all the technologies involved. And below in the figure, you see an example on how this could look like. So here you see a summer week for an optimization on costs for a case study in Crete. And I just want to show you here that it could be quite interesting to see this, right? Because you see that, for example, on the top figure, you see that we try to balance here power demands and power interactions. And you see that different kind of power generators are there, for example, solar PV. We also interact with the grid. And we, of course, also have the demands and so on. And we'll also see that on the secondary y-axis, we have a battery installed, which is, for example, charged with solar PV electricity locally generated. On the bottom figure, you see the high temperature heat provision in this multi-energy system, which is mostly provided by an electric boiler. And for some peak demands, you also see that the diesel boiler is installed. And this was just an example, and I will show you now more examples in the upcoming slides, because, of course, you applied the framework on 2 case studies, both in Eikerøy in Norway and also in Crete in Greece. And I want to show you a couple of results from that to also better understand, what you can do with our framework. So first of all, we applied the framework to Eikerøy in Norway, and Eikerøy is a geographical island of 20 square kilometers in the southwest of Norway, with around 2,400 citizens. Currently, it has a power demand, and the power demand is mainly met by a grid connection with the mainland, so it's grid connected. And the main energy consumption in this island, it comes mainly from the local fish industry. And the energy consumption, which is mostly heat consumption, is currently supplied by a fossil-fueled gas boiler. And it's also good to mention here that actually the electricity supply in Norway is very low carbon electricity. So the main thing to decarbonize over here is the local fish industry. And as I said already before, Robinson Horizon 2020 aims at the full decarbonization of geographical islands with a real demonstration in Aigehoy. And this is quite fascinating to see, because now you see also the real system components installed, of course, in Aigehoy. And we went there last month. And now you see, for example, that have the advanced CHP unit installed, electrolyzer, the ADBES unit to generate biogas and so on. And this is, of course, very nice to see that it's also associated to a real demonstration project. And what Nicolas already said, and I also mentioned, is that we have follower islands in Crete and Western Isla. And as I also mentioned already before, we can design such a system using different objectives. We can, of course, have a cost objective, so we want to design it in a cost-efficient way, or we can design such a system in a greenhouse gas emission effective way. And you could, of course, choose somewhere in between, let's say, by, for example, applying different weights. So then I come to the results for the case of Aigehoy in Norway. And here you see two figures. On the left figure to the bottom, you see an optimization of costs. On the right figure to the bottom, you see an optimization on life cycle greenhouse gas emissions. And you directly see there's a big difference, right? I mean, for cost optimization, you will only install cost-efficient technologies, let's say. You will install still a gas boiler, because when we designed the system, I think in 2021, 2020, natural gas prices were still quite low, and therefore we would still install a natural gas boiler. However, you see that also cost-efficient onshore wind is already installed. I will come back later, on the real constraints which we actually experience, within Robinson. But you also see that we install heat pump, electric heating, and so on, and even some residential heat storage. However, if you run an optimization on greenhouse gas emissions using a framework, as you can imagine, you will install different components. For example, you install even more renewables. You will install the advanced CHP unit, which is able to run on low carbon fuels. So, and in that case, we also integrate an electrolyzer to supply hydrogen to an advanced CHP unit. We install hydrogen storage, the ADBES to generate biogas, and so on. So I just want to show you here that incentive, of course, very much matter, let's say. However, it's also good to mention here, and I'll explain it on the next slide, that you can also have like an objective somewhere in between a cost and a greenhouse gas emission objective. So here I elaborate a little bit more on the results in Aigehoy in Norway. On the left bottom of this slide, you see a figure, which is a Pareto front. So on the y-axis, you see the annual cost, and the x-axis, you see annual life cycle greenhouse gas emissions. And you see different points in this graph. And the business usual scenario, which is abbreviated as BAU, is kind of the scenario which was before implementing a multi-energy system. So there we rely on a fossil fueled gas boiler and of course electricity from the Norwegian power grid. However, if we run our optimization framework, you see that we can run the optimization using cost minimization. So that's the cost min, which of course reduces the cost by the most, like by minus 40% for the entire multi-energy system. And at the same time, it's interesting to see it actually also reduces already greenhouse gas emissions. And however, if we run a greenhouse gas minimization, you see that greenhouse gases can be reduced by 78%, which is quite a lot if you also consider that Norwegian grid electricity is already very low carbon. But what we do mostly here is that we decarbonize the local industry. However, what is very even more interesting, I would say, to see is that we can pick specific points within this graph, right? So you see, for example, that we can pick points in here, like for example, the cost greenhouse gas 90, you can pick this point. And here you can see that the cost increase is quite moderate, while you can still reach a very high decarbonization potential. And this is quite interesting what you can also, of course, reach with using our optimization. And you can, of course, even discover different points within this graph as well. However, this is not the end of the story, because I said already before is that we're not only focusing on cost and life cycle greenhouse gas emissions, right? So the nice thing about our framework is that we can also quantify other environmental burdens. And that you can see on the right-hand side, on the right figure. Let's say you see here, you see here again the business usual scenario. And I would say that the bigger the red area, the more environmental burdens, right? And the specific names refer to a different environmental impact category, which you see here. And we're not going into detail over here, but what is important to recognize here is that, of course, for the business usual scenario, the business usual scenario performs worst on almost all environmental impact categories. However, if we then move to like a greenhouse gas minimization, you see that the environmental impacts are reduced on almost all categories, except land transformation and some human toxicity indicators. And this is due to the integration of biomass. And of course, when you integrate biomass, you also need more land to, of course, harvest biomass and so on. And this kind of trade-offs can be considered, with our optimization framework. And I think that's quite interesting and nice to see, because of course in the future we will move to a low carbon energy system. At least I hope so. But we have to keep in mind that it could also exhibit some environmental trade-offs, for example, related to land transformation or materials. And one other important thing I want to mention here, which you of course also saw already here. So if you run a greenhouse gas minimization, this is really the point that we cannot reduce greenhouse gas emissions anymore. But even at this point, you still see that we have some residual emissions. And for greenhouse gas minimization, what I want to mention here is that embodied emissions, of course, become more and more important, right? Because operational CO2 emissions become less and less. But however, in this case, we have also embodied emissions. And for very decarbonized energy system layouts, embodied emissions become more important and could have a share of up to 60%. So in the end, it's of course also important to include embodied emissions, which we can do with life cycle analysis. So then move to the next case study. So we also applied the optimization framework to Crete, which is in Greece. The multi-energy system considered here is a little bit different, although you can see it's quite similar as the previous one. However, we integrated here also an electric boiler, and we had less focus on residential heating because we don't need so much residential heating in Crete. Again, we included different sectors, energy sectors, the local bakery industry, residential households, and residential mobility. And for this case study, we provide special attention to energy autonomy. And why did we provide additional attention to that? Because currently the power grid in Crete is quite greenhouse gas intensive. So if you don't have a power grid connection, and when you generate all your energy within your own multi-energy system, for example, by offshore wind, onshore wind, solar PV, and biomass energy sources, then of course you can really decarbonize the system. And as I said, with an energy autonomous system, you don't have a connection to the power grid network. And we also provide special attention to local regulations, because in Crete, there are quite strict regulations regarding renewables installations. And we want to show the influence of that as well. I will not go into detail here because for the sake of time, but I just want to show what we found. So also for Crete, we found that we could have like potentially substantial cost and emissions reductions. However, that these cost and greenhouse gas emissions reductions are most likely limited due to location-specific constraints, because in these regions you can, for example, only install a couple of kilowatt peak and megawatt peak of onshore wind and solar PV due to these regulations. And this energy autonomous multi-energy systems could be suitable decarbonization options in Mediterranean regions, only for a marginal cost increase of around 15%. However, of course, also for off-grid multi-energy systems, we also experience some environmental trade-offs, for example, related to materials, because we have to install more energy system components related to energy storage, and we have to oversize renewables. And in addition, of course, if you oversize, let's say, your renewables and energy storage mediums, you also need more investments, which could, of course, also hinder the actual implementation of off-grid multi-energy systems in Mediterranean regions. So now I come to the limitations of our framework. So one of the big limitations, I would say, of our framework is that we use a deterministic optimization approach, which means that we have perfect knowledge of generation and demand. So we could not really consider kind of stochastic energy prices, and so on. And because we have this deterministic optimization approach, this also results that small changes of chosen inputs could have substantial consequences for the optimal design. You could think about this, for example, if I reduce my capex by 50% of solar PV, of course, the optimal design will be totally different, right? And we also didn't consider, for example, potential power grid outages, surge of power and natural gas prices. And including this, of course, would be very interesting because this would of course, increase the robustness of the optimal design, which we not included, unfortunately. Furthermore, we only included one design year, and the design year was, let's say, now in the current year, and it would maybe be more interesting to include multiple design years. For example, a design year now in 10 years, because in 10 years or in 5 years, the situation will be totally different, right? Regarding capex, energy price, and so on. And prospective LCA can then, of course, also be coupled regarding that because we look into the future. Furthermore, we also applied an energy hub approach, which means that we didn't have spatial details where, for example, the technologies will be installed, and we also aggregate, let's say, the demands and the supply of energy. And for the LCA part, we could also have more focus on the end of life because we focused very much on embodied emissions, but end of life was more or less disregarded because of the huge uncertainties over here. Although I would say it would be very interesting to have like a more end of life focus also in the future. As I discussed, for the tool itself, it's currently a Python-based framework, and therefore it's limiting its usefulness for the general audience, I would say. And in the future, we hope to make it more interactive so that also maybe the general audience can better interact with it. So then I come to the conclusions, where I discuss quickly the highlights, key messages, and future work. So, as discussed, we developed a novel optimization framework for designing multi-energy systems, considering different boundary conditions. We considered life cycle environmental burdens endogenously into the optimization, and we considered a wide portfolio of technologies. And I have to say that, of course, this wide portfolio of technologies could be further expanded, and I hope we will be able to do so in the future. We applied the framework on 2 geographical islands, so in Aigehoy in Norway and in Crete in Greece. And what is nice about the optimization framework is that it can showcase the cost and decarbonization potential at an early stage, for example, during design phase. And we could also show potential environmental trade-offs related to that, as well as the influence of location-specific constraints, for example, limiting the amount of renewables in specific regions and so on. However, I talked a lot about optimal design, but of course also in Robinson we found out that achieving such an optimal design is quite unrealistic, because we have so many constraints in terms of regulation, social acceptance, and investment risks. However, we found it still useful to show our Robinson partners, what could be potentially reached regarding cost and environmental burdens, when we have an optimal design. As also discussed, the framework and non-confidential data are published on GitHub, and the explanation of the framework is published in several scientific papers, and we hope that this allows to further develop the framework towards an interactive tool in the future. So potential ideas for future work. So it would be nice maybe to integrate additional novel energy system components and also, of course, to address the main limitations mentioned in the previous slide. In addition, it would be a good idea maybe to create a Python package so it would be used by more researchers, and it would be good to then also, of course, increase the amount of documentation available. And finally, to interact also more with industrial partners and a general audience. It would be very great, I think, to make the tool more interactive on the web. Yeah, and here are the references. So I would like to thank you for your attention, and also would like to thank all partners involved into the Robinson project. It has been really fun to work on this project, and I'm happy to answer any questions you may have. Thank you again.
Thank you, Tom, for the detailed presentation, and thank you for your availability today to present this work that you have been working on over the last few years. And personally, I'm happy to see the advancements in your work. So I would like to open the floor for the question and answers. If you have any questions or comments, please raise your hand identify yourself with the name of your company, and then you can feel free to ask any questions to Tom. Peter, please.
Yeah, hi Tom. So thanks a
Hi,
lot for
Peter.
the presentation. I was wondering, could you give a kind of an estimation about? Sorry, I had this flap closed. Could you give a kind of estimation how what would you estimate in terms of necessary effort to, start a kind of a simulation, putting together all the data and so on? I mean, it took quite a while because it was part of your PhD anyway. But do you have an estimation?
Yeah, well, I mean, of course, we applied the framework now already, right, on two islands, and that, of course, helps, already establishing a lot of data, like, for example, techno-economic data, life cycle inventory data we have now, right? So it's basically about getting the demand profiles, for example, from industry, residential households, and residential households data can usually also be generated by some, of course, repositories, Python repositories on the web. So it's mostly about demand profiles. And then, of course, you have to validate the results, right? And this, of course, also takes time. But I think, it's more about demand profiles and getting this data. And then for the rest, I think it should be doable. So and then in that case, it's not so much work anymore. On the other hand, I have to watch out, right? What I'm saying, because you always underestimate, the amount of work you have to you do in the end, right, to make it work, everything. So, yeah. I hope this answers your question.
And the resolution you need is kind of 1 per hour.
It's hourly data, indeed. So there's a lot of data points you need, indeed, right? And I think this is also great because you get very sophisticated data also out of the optimization. But I mean, you need a lot of data, as you said. But I mean, for a lot of this data, there are already Python packages available, for example, to generate demand profiles for residential households, for generation profiles of solar PV and onshore wind and offshore wind and so on, right? So this could be easily covered. However, like real demand profiles, like for example from industry, that's more tricky, right, to obtain. And usually these demand profiles are also confidential. So yeah, that's more difficult.
Another question in that context, what's about the size of the energy systems? I mean, could you, in the worst case, also look at a kind of single house or small farm application, or?
Yeah, that's a good question. I think I should have mentioned that. So because we have this kind of energy hub approach, right? So basically, for each technology, it's modeled as one technology, which is maybe not really realistic, right? For example, if you have a lot of residential heat pumps for residential households, in our framework, it's modeled as one technology. So one drawback, it's maybe in that case not realistic. On the other hand, as you said, you could apply this framework also on like let's say smaller energy systems, like for example even residential households, right? Or like small communities or even districts, or I wouldn't say like entire nations because they have to involve much more technologies, right? But yeah, you could have different sizes indeed as for your energy system. Yeah. I hope this answers your question.
Yeah, it answers my question, and it leaves me now kind of, I should have done it before I now invested in my PV and heat pump at home, I guess.
Yeah. Well, maybe, I don't know. It could be, yeah.
Yeah.
Thanks for the questions.
Thank you, Peter. I see another raised hand. Bingtian, you, please. Floor is yours.
Thank you for your presentation. I have two small questions. So the first question is, in your mixed integer linear programming, what do the integer variables represent? Are they in the design part, or in the operation part?
So yeah, that's a good question. I go back to the decision variables, right? So they're both in the design part. So for example, we want to make sure that we don't charge and discharge the battery, for example, at the same time, right? So we also have this as an hourly binary variable, for example. But we also have binary variables. So I think actually most in the operation part. As I said, you don't want, for example, to charge and discharge the battery at the same time. But also you need binary variables, which are also hourly, I believe, for the start up and shutdown status as well. And that is, of course, also a lot of binary variables. But as I said, for the startup and shutdown status, we limited these binary variables to a couple of energy system components because these were only applied, for example, to the wood gasifier, because this wood gasifier unit is less flexible in terms of operational behavior, let's say. And also to the advanced CHP unit, because when you, of course, constantly going to switch on and off the advanced CHP unit, of course, it also increased the component degradation, right? So we only applied it to a couple of technologies. And this was for the reason because, of course, otherwise it really increases the complexity of the optimization. So this is, of course, kind of a trade-off you should consider, right? Between complexity and simplifications. And then you, of course, have to decide, okay, is this complexity right to achieve the right results, let's say, in a way, right? So it's a trade-off between complexity and simplifications, and well, I would say trade-off between complexity and accuracy, right? So yeah.
Yeah, thank you. And my second question is that how long does it take to solve one MILP problem with the solver Gurobi?
Good question. So that really depends on the objective. So for cost objectives, as you can imagine, you install generally less energy system components, right? Because you still have some fossil fueled energy system components involved. However, if we run an optimization on greenhouse gas emissions, those optimizations can be very computational expensive. So, I ran it on my laptop. I have a good laptop, I know, but then it can take like 10 to 12 hours for some specific cases, which is a lot. However, I did not run it, for example, on a supercomputer, and so I cannot give an answer on that. So these are the performances indeed. Yeah.
So when you look for the optimal solution, it's the theoretical optimal, or you have set a tolerance gap?
Yeah, so I've set the MIP gap, right? I think mostly 0.5%. Yes.
5%. Okay, thank you.
Something like that, or 1%, but I think 0.5. If you really want to have an answer on that, I can check later. But I think you can also find it in a paper, but it was for sure less than 1%. Yes.
Okay, thank you.
Welcome. Thanks for the questions.
Thank you. Mitro, I see you raised your hand. Please go ahead.
Hi, I have more question about this life cycle inventory data. Is it, you mentioned before, it's from this program or database that you're using, which you need to pay for, and how much time and actual efforts you need to get this data and for different technologies and...
Yeah, good question. So as I said, for eco-invent, you need a license, right? If you want to calculate the LCA impacts of each technology, right? And also for your energy flows, let's say. However, as you could see here in this slide, you could also circumvent this now because I pre-calculated the environmental, let's say the LCA impacts on greenhouse gas emissions for the system components already. So if you set this parameter, wait, I'll show here. I hope you can see my laser point. But if you set this parameter to false, you can use the greenhouse gas emission factors already pre-calculated, right? But however, if you want to do like a full LCA and also focusing on other environmental impact categories, you really have to buy a license of eco-invent, right? And I'm not sure how much it costs, but I think it's around 2 or 3K for one license per year. I mean, if you use a lot of LCAs, then of course it's worth it. But I mean, if you don't use it so much, of course, then it might be also expensive. And you need, of course, this database to calculate the impact factors, right? And yeah, so that's my short question, let's say. Yeah.
And these impact factors, they're scalable, for example, for different technologies.
Yeah, so
or,
that's maybe a drawback of LCA. So LCA is usually kind of linearly scaled, right? So you don't have many, let's say, economies of scale in LCA. However, you could consider that because in a database, you of course have different sizes of energy system components. However, I just linearly scaled it, you know, if the capacity increases. But if you have access to the database, you might also consider having more economies of scale or apply it yourself if you find an alternative source on the internet. Yes. Yeah. Does this answer your question?
Yeah, to some extent. I just
Okay.
was thinking, for example, if we have a batteries, and batteries kind of small one and a big one, it's a bit different, and price and everything, and
True, you're
how they
right.
behave, and
But also, I mean, also prices here. For example, it's per kilowatt, right? Kilowatt hour, let's say,
yeah,
energy capacity. We just apply the same price per unit energy capacity for the battery. Also, if install a large battery unit, and I totally agree, this could be improved, right? Because for larger battery units, you most likely have some economies of scale and so on. So this is something you could, of course, integrate yourself, right? I mean,
yeah.
we did not, and so this is a drawback, and I agree with that. Yes.
Yeah, so thank you very much.
Welcome.
Mohammed, hello, please go ahead.
Hello, Tom. Mohammed Mansouri from University of Stavanger and North. A follow-up question to what Dimitro asked, and that was related to new technologies that Robinson project bring into the table. How did you consider the LCA for those technologies, like specifically the ADBES part, right? How did you simplify the calculation there? Because normally you are basing it on some historical data. And then I guess like, inventory like equipment, they don't have like good and reliable data on such technologies that are still at a, let's say, TRL level of 5, 6.
Yeah, good question. I mean, for the ADBES unit, we just considered an energy flow, which is biogas from waste, and there we got an emission factor for and a cost for, and we didn't consider here the component itself because we didn't get the inventory data for that. However, for the advanced CHP unit, which is of course also a novel system component, we requested the data from the industrial partner, Aurelia, and we got their data. And based on that, we generated new lifecycle inventory, which of course also included into our model in a way. However, this is confidential data, and therefore it's of course also not available in the repository. So for some components, as you said, you know, we have to make like really simplistic assumptions, like for example, the ADBES, we just assume it as an energy flow. But for the advanced CHP unit, we generated novel lifecycle inventory data indeed. Yeah, I hope this answers your question.
Yes, sure. Thank you very much for that. And then I wanted to ask another question, which is like different, and that is related to like, you know, stochasticity, like uncertainties.
Yes.
Can you elaborate a bit more, like, you know, how you can just implement something like that in a MILP like framework that you develop?
Yeah, that's a very good question. I mean, it really increases the complexity of such. It really increased the complexity of your framework because usually you have to integrate additional binary variables to consider kind of the range that, for example, demand profiles can differ, you know, from the actual profiles. And usually to do so, you need additional binary variables, and binary variables usually are killing kind of your computational behavior, you know. And so you can do this, but it also really increased the complexity. So therefore we did not do this, but it would of course be interesting to do some specific case studies, right? To see, okay, what is the influence, right? If we really try to include stochastic elements into the framework, but to make this framework stochastic, that's really tough. And I think you cannot make everything stochastic, maybe only a couple of demand profiles and so on. Yeah, I never tried this, but as I said, because it really leads to additional complexity. But
yeah, sure.
I mean,
like, you know, I would think that it is very difficult, like, to do it like, on every hour of a year, right?
Exactly.
Maybe it is possible for a week ahead of us, because it has like less hours, let's say, and then of course like the computational force will be much less, but not for a full year. I think like, it's extremely difficult.
Indeed. Yeah, I mean, this is also called like rolling time horizon optimization, right? So then from each time step, you optimize it again. So you optimize it again after each time step. And this is kind of a different optimization, because with our optimization, it's optimizing in once, let's say, right? And we optimize for the entire year. But with a rolling optimization, of course, for each time step, you're going to run a new optimization. And this, of course, takes also longer. But in that case, I think you could also consider more stochastic elements as well, as you also mentioned, yeah.
Yes. Okay, thank you very much.
Welcome.
Thank you, Mohammed. Is there any other questions? We still have a few minutes before closing this training module. Also, if you have any comments based on your research or previous projects, feel free to share your experience. I do not see any comments in the chat, nor any raised hands. So just a question to just a remark to all our participants. I just launched a Slido asking for some feedback on our training module. So please feel free to vote with the Slido and provide your feedback. That will be taken into account when we organize any future training modules. Also, both in terms of organization, also in terms of topics, if you have any recommendations, please let us know. Okay, so I think there is no any further questions or comments. So I propose we close this training module, and I would like to thank one again our project partner PSI Tom for the availability to present this work on the lifecycle assessment tool. And we'll also organize very soon another training on cybersecurity that will come in mid-December, and we'll soon we'll soon open the registrations for that. We're also looking forward to welcome you to the next training. We thank you again for your participation, and we wish you a good day. Thank you.